Hello, this is Brian Washburn. I'd like to do a problem using Lagrange mechanics. And this particular problem, consider this. So I call this the spinning hoop or the spinning hoop of doom problem. This problem is actually in your textbook, but it's worthwhile to go over this problem in detail because it's a pretty good problem and it covers a lot of topics we've been talking about. Also, this problem would be very difficult to solve using Newton's equation, so this is a good example of using Lagrange mechanics to solve. So what I have is I have a hoop, and there's a mass bead of mass m on that's constrained to move along the hoop. So this mass can move anywhere along the hoop without any friction. However, the hoop is spun with an axis about the z-axis. Okay. So what I want to do is I want to solve for the equations of motion. I'm going to get the equation of motion for the mass m. In the end, I'm going to get an nonlinear differential equation, and I'm going to look for conditions where I have the frequency of small oscillations. So in my Lagrangian format, the first thing I want to do is I want to figure out the equations of constraint on the system. And once I know the equations of constraint, then what I can do is I can calculate the kinetic potential energies, and then from that I can get the Euler, Lagrange equation, and the second order differential equation. So this is a one-dimensional problem. Let's look at the equations of constraint. So we have a couple of them here. The first thing is that it's constrained to the mass is constrained to the hoop, so its radial distance is r. Now notice when I write this, I have this x, y, and z. This is the best coordinate system to solve this problem is in a spherical coordinate system. Okay, sorry about that. A spherical coordinate system where I have angles r, phi, and r, theta, and phi. So that's the best system. So this is one of the first problems we've seen using a spherical coordinate system. So first of all, the distance, since it's even when the thing spins, the mass is on a surface of a sphere of radius r. Okay, so that means r dot is equal to 0, and also r double dot is equal to 0. Also, the angle, the azimuthal angle, changes at a constant rate. So I can say that phi dot is equal to omega. And that gives me an expression for phi as a function of time, which I'm never going to really use, but that does describe the angle as a function of time. And then, of course, from that, I can say phi dot double is equal to 0. So my one free variable, okay, again, so this is a one-dimensional problem, is theta. All right, theta. Now, just to remind you, we have to write down the expression for this is the velocity in a cylindrical coordinate system. All right, and the reason why that's important is because remember what we want to get is we want to get potential and kinetic energies, and the kinetic energy is always going to be equal to, T is going to be equal to 1/2 mv squared. So that means I have to take the v squared is equal to here v dot v. Okay, and so then what I can show here, now let's rewrite this equation here based on my my equation of constraint. Okay, this first term is 0 because r dot is equal to 0. Okay, the second term is going to be equal to r times theta dot theta hat, and then the other term is going to be equal to r sine theta, and then we have this phi dot, but phi dot is omega of that right there. So then what I can do is I can calculate the square of that, or v dot v. If I get that, I'm going to get here r squared is going to be r squared theta dot squared, sorry, plus r squared sine squared theta omega squared. So that is my velocity, or speed squared, I should say, and that's going to give me my kinetic energy. So let's calculate the kinetic energy and the potential energy. Okay, so what I'm going to do is I'm going to find the kinetic and potential energy. We wrote before that going back to here, the kinetic energy is T is going to equal to 1/2 mv squared, but we showed that what v squared was, so just writing that, it's going to be equal to 1/2 m times v squared, which we got before, which is
r squared theta dot squared. And then we had, so then actually let's just multiply 1/2 mv squared out by all that. So we're going to get that term there plus 1/2 m times the other part is going to be r squared sine theta squared omega squared. So that is my kinetic energy. Potential energy, I have to define zero potential energy. I'm going to define it at the bottom. So I have my hoop here, and I'm going to find that point right there equal to zero potential energy. Potential energy is going to be mg, the height. So if this thing is here, this is a height here. And that's just going to kind of look like a pendulum. That's going to be mgr 1 minus cosine of theta. Okay, so now I have my kinetic potential energies. Now I can write down my Lagrange, and my Lagrange is going to be equal to T minus U. And then I'm going to have all this stuff here. Okay, so that's not too bad. And again, the natural choice of solving this is using a spherical coordinate system. And because the radius doesn't change, minus mgr 1 minus cosine. Okay, so that's what I have. Now what I'm going to do is I'm going to use that expression and then get the Euler-Lagrange equation. Again, it's one-dimensional. So again, we're going to take the partial L with respect to theta dot. There is only one theta dot term. So that's going to give me m r squared. The 2's cancel out, and I'm just going to get theta dot there. Then I'm going to take d dt of that term there. Mass is constant, r is constant. I'm going to get m r squared theta double dot. So that gives me the angular acceleration. Okay. And then the final term is partial L respect to theta. And there's a bunch of thetas there, so that's the harder term. Here I'm going to get sine squared times 1/2, so that's going to give me omega squared mr squared. Then I have to remember what I have to do is I have to take the derivative of sine squared. That's going to give me 2 sine, and then the derivative of sine is cosine. The 2's cancel, the 2 cancels out with the 1/2, so that's going to give me, sorry, so it's going to give sine theta cosine theta. Okay, now I don't have theta dot here, remember, since it's a partial derivative. And then finally I have this last term, minus mg r times minus cosine, and only cosine, so that's going to give me minus, it gives me a plus, but the derivative of cosine is minus sine, so that gives me another minus mgr sine theta. Okay, now we put that into the Euler-Lagrange equation, or really, it's not really called in this point, I would call it the Lagrange equation. It's really its appropriate name. So I have all the stuff there. And then that's going to give me minus omega squared mr squared. It's from that term, so it's minus. Okay. Sorry, I made a mistake. There is no minus sign there. So we got that. And then we have omega cosine, and we're going to get cosine theta sine theta minus mgr sine theta. That's important. Mgr squared theta double dot. Then let's just write this all on one side. Divide by mr squared. If I do that, I'm going to get theta double dot. I'm going to get here minus the mr squares cancel out, omega squared, cosine theta, sine theta, plus g over r sine theta equals 0. Okay, that's my equation of motion. Now you can check it. The way you can check it is if you set omega equal to 0, that means the hoop doesn't spin. Then you get theta double dot plus g over r sine theta. That thing looks like a pendulum. So basically the mass in the hoop acts like a simple pendulum, and the nonlinear restoring force is, the sine theta component. That's the restoring force. Okay. Now we can. So we solved the equation already. So we have my equation of motion. But now what we can do is we can look at equilibrium positions and also the frequency of small oscillations. This is actually a fairly rich problem. Let's take a look for equilibrium positions. Again, what we're going to do is get my differential equation looked like this here. Okay. And so in order to find equilibrium position, I'm going to set theta equal to theta naught. That's my equilibrium position. That means theta double dot's equal to 0. If I do that, then I'm going to get an equation that looks like this. So notice I have minus omega squared cosine theta naught sine theta naught times g of r sine theta naught. I'm going to factor out a sine theta naught. So I get sine theta naught times this stuff here. Now, technically, there's 3 roots to that equation. Remember, sine can equal 0 where theta naught equals 0 or theta naught equals pi. So that's at the those two equilibrium. If you think about those two equilibrium positions, you got hoop here, and one equilibrium position's here, one equilibrium position's there. Okay. Now the one on the bottom is going to be stable. The one on the top is actually to be unstable. However, there's a third one, and that third one comes from this equation right here, and so that's going to be at some angle. Okay, that is again, again, let's just draw it out. So again, I have a axis that kind of comes up through here. Here's the center, and then I'm going to have some other equilibrium position, say here. That equilibrium position, notice that equilibrium position is the arc, or the cosine of that is g over r times omega naught. Okay, or we can this is omega c as for the simple harmonic motion. For pendulum, this g over r. So it's just a ratio of omega c squared over omega squared. Now, if you plot theta as a function of frequency, okay, the frequency omega that I spin, remember omega, what is omega? Omega is the angular speed like that. If you plot that, let's take a look at that real quick. You can see here that this, again, I'm plotting the arc cosine. There's some values of the arc cosine is not defined, but once I'm above a beyond a value, I get an omega c. So once omega is bigger than omega c, then cosine or arc cosine is defined, and this thing, as I increase omega, asymptotically goes to pi. That's really cool. Oh, pi over 2. So what that really means is that, if I spin this thing, I might have an equilibrium position here. Now say I spin it faster. If I spin it faster, what's going to happen is this guy is going to asymptotically get to an angle of 90 degrees. Okay, but never get there. So those are the 3 equilibrium positions. Let's now find the frequency of small oscillations. Okay, so I'm just going to show you, again, we've done this multiple times. What we're going to do in solving the frequency of small oscillations is set theta equal to the equilibrium position plus some small angle. I said theta dot equal to delta dot, and then theta double dot equal to delta double dot. I stick that into the differential equation that we had. Now notice I get cosine theta naught plus sine plus the cosine theta plus delta, sine theta naught plus delta. Okay, and then same here. At this point, what I'm going to do is I'm going to break up the cosines and sines into using the small angle, using the angle relationships. Okay, and then use the small angle approximation to order delta. I'm going to drop delta square terms. So we did this before with the pendulum that was moving with a constant acceleration. So cosine of theta naught plus delta, using the sum angle, we got cosine theta naught, cosine delta, sine minus sine theta naught, sine delta. This term here is using the small angle approximation to first order is 1. And then this term here, using the small angle approximation, is delta. We do the same thing here, except what happens is cosine, I get cosine delta here, which I treat as 1 here. I get sine delta, which you treat as delta. I stick all this back into here. So then notice I get kind of a complicated, I have to multiply these two polynomials together. Okay. If you can go through the algebra doing that, you're going to get a group of terms that looks like this times delta. That will be the frequency of small oscillation squared. And then I'm going to get, when I multiply this term times this term, I'm going to get delta squared. I'm going to get this term here. I'm going to drop that again because I'm going to ignore terms of delta squared. And then this is the equilibrium position, which I'm going to set is equal to 0. So thus I have my differential equation looks like simple harmonic motion with this is my frequency of small oscillations. Now we can rewrite that expression a little bit more succinctly. Remember cosine the equilibrium position is equal to omega c squared divided by omega squared. I can write a little right triangle here. That gives me sine just using this expression. And then instead of writing cosine and sine, sorry, there should be a theta naught there. I can write it all in terms of, get rid of theta naughts and just write it in terms of omegas. And so I get a very simple expression that looks like, this thing looks like omega naught, because that's the frequency of small oscillations. Looks like the dry frequency is sine times some term like this. Okay. So let's take a look at that term. We'll plot that term. So we can finish up by just actually looking at the motion itself. So what we saw was, okay, so let's take this hoop and let's spin it and let's increase the angular speed that we spin it. If we're spinning it relatively slow, meaning that omega is less than omega c, it's going to have one equilibrium position. And that equilibrium position is going to be at theta equals 0, and it's going to oscillate about that point. However, once I increase theta beyond theta c, again, omega beyond omega c. Remember, omega c is the square root of GL. It's the natural frequency of a pendulum. Okay. Then what happens is there's a possible second equilibrium point. And however, that equilibrium point is not constant and will increase with increasing phi. But also the frequency of small oscillations increase as well. So if I increase this, so say I have a small omega, say I have omega, but it's small, but it's bigger than omega c. This thing is going to have an equilibrium position here. It's going to kind of oscillate about that point for small frequency oscillations. But once I increase omega, the equilibrium point gets closer and closer to the pi over 2, and it will have a larger frequency of oscillations. In fact, as omega goes to infinity, the equilibrium position goes to pi over 2, and the frequency goes to infinity. So it gets closer and closer as you spin it faster. The equilibrium position goes closer and closer to 90 degrees, and the frequency goes up to infinity fast. So we actually described this motion of this pendulum or this system pretty well for many degrees of spinning it without actually solving the differential equation. Okay, so that's it. We'll talk to you later. Bye-bye.